Good morning. This is your chemistry video lecture for Monday, September 21st. Today, we're going to take our ideas we were learning last week about measurement and errors in measurement and show how that applies when we do our calculations. Now, this is going to be a little bit dry. We'll do the best to make it interesting, but I really want you to see why it is important. And about halfway through today's lecture, you will see that. All right. So let's get right to it. We're talking about significant figures today. Significant figures. What does significant mean? Significant means important, right? So these are the numbers or the figures, the digits that are important when we make a measurement or a calculation. It helps us understand how accurate our measurement is, right? So if we go back to last week a little bit and talk about what were we doing? Right? We were taking rulers, we were taking graduated cylinders, we were measuring things. And we talked about how when we use one of our tools, we look at the tick marks, the little increments on there, and we always have to estimate one digit into that, right? So if we have a ruler and it's got tick marks every 1/10 of a centimeter, right? So the 1/10 of a centimeter, we have to estimate one more digit. We have to estimate to the 100ths of a centimeter. Now, because their measurement is all measurements have errors, right? Because all measurements have errors, that's why we need our significant figures. It tells us how good our data is. So if we look at this bottom ruler, right? It's got tick marks, every 10 tick marks every 10 centimeters. The one above it looks like it has one tick mark every centimeter. So the scale's not quite the same. But what you want to do is look at how big each increment is, right? Now your calculator, if we take your calculator and let's divide 4 by 6, right? That's 2/3. It's going to come out to be 0.66666. It's going to have a whole bunch of 6s and a 7 because your calculator is not doing a measurement. Your calculator just is doing math, and it's just only doing math. It's not trying to do anything to tell us what the significance is, how accurate things are. So calculators don't care about significant figures. We do. Humans do, because it helps us understand how good our measurement is. Now, one point, as it's at the bottom of the slide, if we're doing a multi-step math problem, I want you to use sig figs throughout the entire problem. Don't drop them partway through. Always carry that sig fig all the way through the problem. And I'll explain that a little bit more when we start doing some of our examples. Quick review from last week as well. Exact numbers versus estimated numbers. Hopefully remember the exact numbers last week. These were things that are counted, right? Like 5 dimes. I think I used the example sheep last week. We can't have a partial sheep or a partial dime. It just doesn't make sense, right? I guess you could cut them in half, but that's not a very realistic way of counting dimes or sheep, right? So counted numbers are exact. They have an infinite amount of precision in them. Givens. So if I tell you there are 12 inches in a foot, that's exact. Right? We can assume there's an infinite amount of precision in it because it's a definition. Right? Constants. If we have constants like the 1/2 in the area of a triangle, the 1/2 times the base times height, that 1/2 is an exact number. We can think of an infinite number of digits on there, infinite amount of precision. And conversions. Whenever I give you conversions, like 2.54 centimeters to an inch, we'll consider those to be exact as well. So those 4 things we're going to consider exact. Notice none of those are measurements. None of those are measurements. And that's the key thing here. That's the key thing. If it's in a measurement, it will be in it. There'll be some estimate in it. There'll be some error in it. And that's why we need sig figs. Right? Estimate numbers are observed, right? We look at it. We look at a ruler. We look at a graduated cylinder. It's something we are looking at. And then we are making a measurement and an estimate of how that quantity matches up. Okay. So let's talk about the difference between exact and estimated numbers a little bit further. What I'd like you to do here, let's look for this worksheet together. And I want to look at each of these numbers. And we're going to figure out whether they're exact numbers or an exact quantity or an estimated measurement. So I want you to always keep in the back of your head, is it something we're measuring? Or is it something else like that we're counting, or it's a constant, or it's a given? Okay. So let's start off with 132 people. Is that something we measure, or is that something we count? Well, we count people, right? So we would call this an exact number. An exact number. We actually would go through and count the 132 people. Right? Something that is 800 miles long. 800 miles long. Well, are we going to count miles? No, miles is something that we measure. So this one's going to be an estimated number, right? It's a measurement, something we estimated. 76.00 degrees Celsius. Let's look at the next one. Is that something we measure? Oh, absolutely. It's something we measure. That will also be estimated. Let's look at the next one. 1,000 milligrams equals 1 gram. Well, that really can't be a measurement. We got two different things in there. And that's right. This is not a measurement. This is a conversion. Right? It tells us 1,000 milligrams is equal to 1 gram. This is going to be an exact quantity. All right. 2.54 centimeters equals 1 inch. Just like the one above it. It's a conversion. It's not a measurement. It's a conversion between one unit and another. We're going to consider this an exact quantity. Okay. Let's go to the top of the next column, 24.1 centimeters. Right. Well, again, there's only one unit here that I want to contrast to the bottom of the last column. It had 2 units, the centimeters and inches. Here we just have centimeters. Well, do we count centimeters? No, we're going to measure centimeters. So this one, again, will be an estimated number. 10 dimes. Do we measure dimes? What would you use to measure dimes with? No, we count dimes. So this is going to be an exact number. Similarly with a dozen eggs, right? It's not something we measure. It's something we count. So we're going to call that an exact number as well. 10 millimeters equals 1 centimeter. Right there, again, you see 2 different units of measure. This is going to be a conversion. This will be exact. It's not a measurement. And finally, the bottom, we say about 39 inches equals 1 meter. Well, hopefully about is going to tell you that there's an estimate here. We're not exactly counting things. We don't have an exact definition. We don't have an exact conversion. And as soon as you see about, you know that it's an estimate. Hopefully that helps. If this doesn't make sense, please reach out to me. I'll need you to get really grounded in the idea that measurements are estimated, other numbers are not. Anything else that's not a measurement, like counting or a conversion or a definition or a given, those are exact. Measurements are the only ones that are estimated. Okay. Now we'll get into a little bit of the heavier stuff. And we'll try to do this a little not so boring, but it is a little bit dry. And again, the whole idea we're after is how do we know how exact, how precise our measurement is? Okay. So there's going to be 3 sets of rules here. There are a couple sets of rules here we're going to talk about. The first one's hopefully pretty easy. Anytime we have a number that's non-zero, what do you mean by non-zero, right? It's 1, 2, 3, 4, 5, 6, 7, 8, 9. Any one of those digits that we're used to. As long as it's not 0, we're going to count that as a significant number, a significant figure. Right? So what does that mean? Let's go look at this. 247 centimeters. 247 centimeters. There's not a 0 in there. So this must have been something we were able to read up. We could read all those numbers. So this ruler or this instrument probably went down to tens of centimeters, and we estimated that next digit, that units, that ones of centimeters. So 247 centimeters, all 3 are non-zero. All 3 of them will be significant. How about the next number? 0.1491. Again, if they're all 4 of those are non-zero, this one's going to have 4 significant figures. And our bottom one, there are 5 numbers there. All 5 of those digits are non-zero. This has 5 significant figures. All right. So this bottom one has 5 digits. That's pretty precise measurement when we get to 5 digits. Okay. Let's look at our next rule. Zeros are the harder ones. Zeros are the harder ones, but I'm going to try to point out where's the really important one that I want you to see here, because one of them is a little trickier than the other 2. So there's 3 different kinds of zeros, or 3 different ways of classifying our zeros. And the first one, we're going to talk about leading zeros. What's a leading zero? Hopefully the idea of leading, beginning, it's at the front, right? Any numbers that are at the front, any zeros at the front, these will not count as significant. It's not something we read off of our measuring tool. So if we look at these few examples here, 0.0000543, those 4 zeros at the beginning, our tool didn't tell us what those zeros were. Our tool told us that we had the 5 and the 4 and the 3. Those are the significant digits. Those first 4 zeros are not significant. Our leading zeros will never, never, never be significant. Easy enough rule, hopefully. If it's a leading zero, not significant. So when we look at this 0.0000543, even though there's 7 numbers there, 7 digits there, those first 4 are zeros. They're not significant. We only have 3 significant figures here. Our second number, 0.093, again, these are leading zeros. They do not count as significant. Right? There are only 2 significant figures here. And finally, our last one here, there's a whole slew of zeros there. And then finally a 1. Again, none of our leading zeros, right? You're not going to read those off of your instrument. None of those leading zeros are going to be significant. Right? So this only has 1 significant figure. Even though there's a lot of digits there, all those leading zeros do not count as significant. Again, I want you to have in the back of your mind, we're thinking about measurements. Right? Our second group of zeros is also pretty easy in that they always follow the same rule. And here we're talking about captive zeros. What's a captive zero? These are zeros that are in between some non-zero numbers. Here's some good examples. 7004, 7004, those zeros are captive. They're in between 2 non-zero numbers. They're in between a 7 and a 4. They will always be significant. Right? So that 7,004 centimeters has 4 significant figures. Our 1.00088, this has 6 significant figures. Again, those zeros are in the middle. They're captured. They're surrounded, whatever word you want to use, but they're always going to be significant if they've got non-zero numbers around them. So it'll be 6 here. Right? I want you to think about, look at the number right above it, right? That 0.093. There's not a number, there's not a digit in front of these zeros. Right? So these zeros here are leading. They do not count. These zeros in our 1.00088 are captive. They're surrounded. They do count. And finally, our 43,006. Again, these zeros are surrounded by non-zero numbers. They will count, and we will have 5 significant figures here. Again, measurement. Think of your measurement. If we're able to measure this down to 6 kilometers, down to the individual kilometer, that means all these other numbers above it are going to be significant. Think about the measurement. Here's the hard one, and I'm going to try to hope that I can tell you this in a way that makes it simple. Makes it easier for you to remember. And that's putting it at this. Trailing zeros. So we talked about leading zeros, zeros at the beginning of a number. We talked about captive zeros, zeros in the middle, right? They're surrounded by non-zero numbers. There's one group of zeros left, and that's what we call trailing zeros. These are zeros that are at the end of a number, all the way to the right side of a number. Now, these zeros only count if there is a decimal. Yes, there's a decimal. Yes, these zeros count. Okay. If there's a decimal, yes, count. So 10.0, there's a decimal. Those zeros are going to count. This is us looking at our tool. Let's say it's measuring meters. Our tool can measure down to the individual meters, and we're estimating that 1/10 of a meter. So we can read this right off of our tool, 10 meters, and we estimate to the 10th meter. 1/10 of a meter, right? 0.15430 centimeters. Oops, sorry about that. There's three significant figures there in that first number. 0.15430. Yes, there is a decimal. Yes, that trailing zero, the one on the right, that trailing zero will count. So we have 5 significant figures here. This last one's a little trickier. I want you to look at this. 100,000, but there's a decimal point there at the end. There's a decimal point there at the end. What does that tell us? Right? That tells us there's 6 significant figures here. So I want you to think about this way. Maybe this will help a little bit too. If we were to use our tool, right, what's this telling us? That decimal point at the end tells us that that last zero, that zero in the ones place, the units place, is significant. So what would be the next number we could read off of this tool? It'd be 100,001. 100,001. That would be the next unit we could read, next number we could read off with this instrument. It's very important, right? That number of significant figures tells you where your digit is that could be off. And it's the last digit in this place, in this one, okay? 6 significant figures there. Now, if there's not a decimal, no count. Hopefully this will make it easier. Trailing 0, the ones on the right, yes decimal, yes count, no decimal, no count. So let's look at these examples. 100 milligrams, no decimal, no count, that trailing 0. Okay. No decimal, no count, that trailing 0. There's only one significant figure here. So at 100 milligrams, what would our tool, if our tool can only read to the hundreds, what's the next thing our tool could tell us? 200 milligrams, right? Because it only can tell us that 100th position. It can't tell us the 10s or the 1s. So the next measurement we would get from this tool would be 200 milligrams. This is not very precise. I really want to contrast that with the 100,000 milligrams that are over here. This decimal point tells us we do have a pretty precise instrument. It can measure to the units place in grams. The next unit here would be 100,001 because it has that decimal. It tells you those zeros are all important. They're all significant. The 100 milligrams, no decimal, those zeros are not significant. What's the next number this tool can read? 200, because this is our only significant figure. That's why significant figures are important. This really kind of brings it home, I hope. Let's look at our next one, 1,960 kilometers. We have the first 3 digits are non-zero. They're all going to count. We have a 0 at the end, but no decimal, no count. There's only 3 significant figures here. And then finally, our last one, again, trying to drive our point home of why significant figures are important, right? This one has no decimal point. That means those 5 trailing zeros do not count. There's only one significant figure here, 100,000 grams. This bottom one here, if we were to do a next reading, it would be 200,000, right? It makes that big jump because those zeros aren't significant. We don't know how accurate they are. This bottom tool, not very accurate. The one above it, 100,000 with a decimal point at the end, tells you it's accurate. That means the next number we could read is 100,001. So I really want to hope that we can get this clear, that the decimal point makes a huge, huge difference when we're talking about a trailing 0. And only trailing zeros, right? Leading zeros do not count no matter what. Captive zeros count no matter what. Trailing zeros are the only ones we have to figure out, does it count or not? And I really want you to keep thinking in your mind, what's the next number we could read off of our tool? And I think that'll help you as you try to understand how many significant figures we have. So let's do a couple here. I'll have this worksheet in our folder for today, and I'll do a few, and then I'm going to want you to try the rest on your own. I'll put an answer key out on this later in the folder too, but please try these. These are hard until if you've done a few of them, then you're going to start seeing it's easy. But if you don't try them, you're never going to, it's always going to be hard. So please do a couple of these on your own. It says to circle the significant figures. Let's look at 137. All 3 of those are non-zero. Easy. They all count. They all count. Let's look at our next number here. Okay, I put a box around, so all 3 of those are going to count. Let's look at our next one, 2.49. All 3 are non-zero. All non-zeros count. We have 3 sig figs here. Let's put a square around them. It's easier to put a square on my sheet than a circle, sorry. Let's look at 101, the next one, 101. Well, we do have a 0 here, but what kind of 0 is this? This is a captive 0. There's a non-zero digit to the left and a non-zero digit to the right. That means they are all significant, right? So this one's going to have 3 significant figures. The non-zero, that captive 0 rather, does count. It's surrounded. How about the last one? This was one of our trickier ones. We have a trailing 0 here, right? We have a trailing 0. What's our rule for counting trailing zeros? Yes decimal, yes count. No decimal, no count. Here we have no decimal. That means that last 0 there is not going to count as a significant figure. We only have 2 sig figs here. It's the 8 and the 1. Okay? I want you to try the rest of these. Please try the rest of these and then look at the answer key that I have included in today's notes. Okay. Oh, actually, I'm going to do a few more, sorry. 620, right? Again, we have a trailing zero, no decimal. That means no count, only 2 sig figs here. But the next one, 26.10, trailing zero, it's on the end. Is there a decimal? Yes. Yes, count that zero then. So it'll be 4 sig figs here. The next one here, these next two I'm going to be a little bit trickier, so I want you to be careful as you look at it. What kind of zeros do we have here in this 0.002? Are they leading? Are they captive? Or are they trailing? Well, there's not a non-zero number to the left of them, so they're not going to be captive. They're on their left by themselves. These are leading zeros. What do we know about leading zeros? Does a decimal point impact them? No. Leading zeros will never count. Doesn't matter if there's a decimal or not. A leading zero will never count. Right? There's only one significant figure here. Let's look at our next one. 0.00110. Wow, now we're getting a little bit complicated here, but I want you to always be think about measurement. What are we measuring? How accurate is our tool? And what do we see here? We've got some leading zeros. That first 3 zeros, 0.00, those are leading. They're never going to count. What about the zero at the end on the right? It's a trailing zero. What do we know about trailing zeros? If yes decimal, yes count. This one has a decimal. We're going to count this trailing zero, and the leading zeros will not count. We have 3 significant figures here. Our trailing zero, 1, 1, and the trailing zero, because yes, there's a decimal. Okay. Again, I want you to do the last two here. Try these on your own, and then check your answer against the answer key in today's notes. One last thing today, and hopefully this will catch you off guard, but when you think about it, it'll make a little bit of sense. If I tell you that we're going to multiply these numbers together, 3.0 times 4.0, I'm going to tell you the answer here is 12. Okay? The answer here is 12. Let's look at our next one. So this is kind of a tricky. I want to see if you can follow what I'm doing here. Let's look at the next one. 3.00 times 4.0. Again, I'm going to tell you the answer here is 12. Remember, we're not in math class. We're in science class. So these decimals, these numbers are important, right? We're talking about significant figures here. The decimal tells you something. When we have a trailing zero, that decimal is important. So let's look at the next one. 3.000 times 4.00. I'm going to tell you this one is 12.0. 12.0. And let's do the next one. 3.000 times 4.000. 12.00. So I want you to look at something here with me. Do you see a pattern? Do you see a pattern here? It's a little subtle. It might be hard to see. But I want you to look at this. Look at your top one here. This 3.0. How many significant figures do we have here? 2. How many significant figures do we have here? 2 in the 4.0. How many significant figures do we have in our answer? 2. Let's look at our next one, 3.00. How many significant figures? There's 3 here. Right? The decimal means those 2 trailing zeros count. There's only 2 here in our 4.0. How many significant figures do we have in our answer? 2. So 3 sig figs times 2 sig figs gives us 2 sig figs. Let's look at our next one here. 4 sig figs, right? Those trailing zeros count because of the decimal. 3 sig figs. 3 sig figs in our answer. All right. Trying to point that out a little bit, stating it that way. Do you see a pattern? Do you see how we get 4 sig figs here in our next one? So let's try this. What do you think this bottom number is going to be in science class? We're not talking about math class. We're talking about science class. 3 times 4. Tell you your answer here is 10. 10. And you're going to look at me, Dr. Yates, you're nuts. My calculator tells me 3 times 4 is 12. And I'll tell you exactly right. Your calculator tells you that it's 12. That's math. Science has to take it a step further. Science is interested in the measurement error. So how do we do this? We have to use the right number of sig figs. We have to use the right number of sig figs. 3 only has 1 sig fig. 4 only has 1 sig fig. I'll tell you the rule here in a second. That means our answer only can have 1 sig fig. 1 sig fig. And there it is, the 1 here in the tens place. Tells you the 1 sig fig. Now we had to round it, right? We had to just get 12. Our calculator tells 12. We have to round it. What would you round 12 to? Would you going to round 12 to 10, or are you going to round 12 to 20? We're going to put the 2 there. We'll tell you to round it down. So we're going to round it to 10. So here is the rule. I don't want to show that to you because I think it's tricky. Here's our rule. The number of sig figs in the weakest measurement, the one with the least amount of sig figs, controls or limits how you round. So if we have a number that's got 3 sig figs and we're going to multiply it by another number that has 2 sig figs, 2 is the smallest number here. That means we're only going to allow to have 2 sig figs in our answer. So you need to look at the number of sig figs in each of your numbers. The smallest number of sig figs, the weakest one, tells you how many your answer is allowed. So let's look at our next example. 6 sig figs times 2 sig figs. Well, 2 again is the weakest. That's going to be how many sig figs we're allowed. 3 sig figs times 3 sig figs, our next one. 3s, both of the 3s, it's fine. The smallest number there is a 3. Our answer has 3 sig figs. So what do you think the bottom one is here? 6 sig figs times 1 sig fig. Hopefully you said 1 sig fig. We got to take the smallest number of sig figs when we do our multiplication. That means we have to be careful though, because we have to round when we're done. So be careful how you round. So let's look at this one. Please do this math problem, 135.82 times 17.00. Now, if you put that into your calculator, what's your calculator going to tell you? 2308.94. Awesome. How many sig figs do we have here? We've got 135.82. Those are 5 sig figs in this number. 17.00, trailing zeros here with a decimal. Yes, decimal. Yes, count them. So we have 4 significant figures here. So if we take our answer and we put them in your calculator, we get 2308.94. And I ask you to tell me this to 5 significant figures. What I'm telling you is I need you to round this 2308.94 to 5 significant figures. Here's how I want you to do it. I want you to count out 1, 2, 3, 4, 5. So this 9 is our 5th significant figure. We're going to round it there. What are we going to do that 9? Are we going to round it up or down? Well, the 4 to the right of that 9 tells you you're going to round it down. So we're just going to, this number to 5 sig figs will be 2308.9. 2308.9. Right? To round it to 5 sig figs, we have to go to our next number, our 6th sig fig, and that'll tell us whether we're going to round our 5th sig fig up or down. 4 tells us we leave it alone. We leave it as 0.9. Let's do the same thing. Let's round this to 4 significant figures. So we're going to count off 4, 2, 3, 1, 2, 3, 4. Our 8th is our 4th. Our number 8 here is our 4th sig fig. What does the next number to the right tell us to do? The 9. That tells you we got to round that 8 up. So here to 4 significant figures, we have 2309. Let's look at 3 sig figs. So I want you to count out the 3 numbers, 2, 3, 0. What's the next number tell you? What's that 4th number tell you? 8 tells you we have to round up. So if I ask you to give me this number in 3 sig figs, you'd say 2, 3. That 0 rounds up to 1. But don't forget your 0 here. Don't write 231. That means you moved your decimal. Never, never, never move your decimal. If you need to round something, and you might have to put a 0 in here like we did here so we don't move our decimal. Please do not move your decimal. That will give you the wrong number. Just want you to think about that. Don't move your decimal. If you need to put a 0 in, put it in. Let's look at 2 significant figures. 2, 3. What's our 3rd one? Our 0. It tells us we leave our 3 alone. What's our number here? Remember, don't move your decimal for me. So we're going to put our 2, 3. Those are our 2 sig figs. But don't move our decimal. How do we keep our decimal in the right place? We got to put 2 zeros there at the end. Now again, notice when I wrote this with 3 sig figs, there's no decimal point. It's implied here at the end, but I didn't write it. So that tells us we have 3 significant figures here. That 0 is not significant. Same thing with our next one, 2300. There's no decimal, so these zeros are not significant. This number is only significant to 2 digits. But the decimal is implied there, so we know it's 2,300, not 23. I don't want you moving that decimal, whether it's present or whether it's implied. Right? And finally, 1 sig fig. Right? 2 is our first sig fig. We look at the next number, that 3, that tells us we don't do anything to it. We leave the 2 alone. And don't move your decimal point to 0, 0, 0. Right? Okay. I don't want you just chopping your number. I don't want you just chopping your number. If you look at 4 sig figs here, the answer was 2309. We have to round. It wasn't 2308. We didn't just chop off this 0.94. We rounded. So I want you to be careful with rounding. Rounding, you guys should be comfortable. Hopefully you've done that in math class a long time and often. Here, I want you to be careful about rounding, and then don't move your decimal. So here's a couple quick calculations here. I'll do a few, and then I'll ask you to do the rest. For practice, again, the answers will be in the answer key. So we're going to take this first one, 18 times 3.21. What do I want you to do? I want you to tell me how many sig figs are in each number. Right? So 18. So I'm sorry, your calculator is going to tell you that's 57.78. Let's look at how many sig figs we're allowed. Our first number here has 18, only has 2 sig figs. Our second number has 3 sig figs. So we have to take the smaller of those 2 sig figs, which is 2. What do we do that 57.78? What do we do? We need to have it to 2 sig figs. So 5, 7, those first 2 numbers, there's our 2 sig figs. What's this point? What's the next one tell you? What's this 7 here tell you to do? That tells you need to round the previous number up. So our answer here is going to be 58. 58. Let's try another one. You punch 84.07 times 260.00 in your calculator, and it's going to come back and tell you nicely 21,858.2. Again, your calculator is just doing math. It's not doing science. It doesn't care about measurement errors. Science we do. How many sig figs in this number? 84.07. Well, there's a 0. What kind of 0? Captured 0. It always counts. So we have 4 sig figs here in this number. How about our next number, 260.00? Trailing zeros here. Yes, there's a decimal. Yes, we count them. This one has 5 significant figures. We only have 4 here, so that tells us that's what our answer has. It has only 4 significant figures. So now we got to round 21,858.2 to 4 significant figures. Again, how do we do that? We count off the first 4, 2, 1, 8, 5. We're going to keep those numbers. The next one, that 8, what's it tell you? It tells you we need to round the previous number up. So this 5 becomes a 6. But don't put your decimal point right after that 5, because there's still another place here. Our 8's going to become a 0. And then we will have the decimal at the end. But here, we can't put the decimal point there, because what happens if we do? If we put a decimal point here, that tells us that this 0, this trailing 0, is significant. It's not. No decimal, no significant. This is how you're going to write 21,858.2 to 4 significant figures. 1, 2, 3, 4. 2186, those are our 4 sig figs. Okay, little tricky. I really want you to practice these. Think about how many sig figs you have. Think of where your decimal point is. Don't move your decimal point. Don't move your decimal point. Okay, let's do one more. Punch these 2 numbers in your calculator, you get 0.029964. How many sig figs are we allow, guys? 9.988 tells you there's 4. 0.003, what kind of zeros? They're leading, they don't count. We only have 1 sig fig here. We got to round our 0.029964 to 1 sig fig. Well, what's our 1 sig fig? Remember, our leading zeros don't count. 2 is our first sig fig here. What's the next digit tell you to do? That 9 tells you to round it up. So here's our answer going to be 0.03. Right? Now, why didn't I put zeros here at the end? Because we didn't need those zeros to keep our decimal point where it was. We didn't need to add zeros here to keep our decimal point where it was. And besides, if we did add zeros, that would imply that they're significant, because it has a decimal point in our answer. Right? So you got to be careful. Take your number, round it. Then you got to make sure that however you wrote it doesn't move your decimal point. If you need to zero fill, like we did on the previous one here, put the 0 in. If you don't need to zero fill, don't put it in. Okay. Right. Division is going to be following the same rules as multiplication. Count how many sig figs in each number. That's how much your answer is allowed to have. I'm just going to show the answers here to the first one, and you look at. I want you to try a couple of these and look at the answer key. That's 14.300 divided by 6.1. Calculator gives us this huge long number. How many sig figs are we allowed? 14.300. Trailing zeros with a decimal. Yes, they count. There's 5 sig figs here. 6.1. There's 2 sig figs here. We got to take the smallest one. That's 2. So we're going to round our 2.34426 yada 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 to 2 significant figures. Let's count them. 2 is the first one. 3 is our second one. So we're starting off with 2.3. We have to look at the next number, 4. What's it tell you to do? 4, that tells you to leave the 3 alone. Our answer here is simply 2.3. Okay. Same rules as multiplication. Count your sig figs in each number. Smallest number of sig figs wins. Look at your calculator's answer. Round it to that number of sig figs. Okay. I'll show you the next one here. You get a nice long number. How many sig figs are we allowed? 0.63.0, trailing 0 with a decimal. Yes, it counts. 3 sig figs, 15.22, 4 sig figs. So we're only allowed 3 again. Count them off. 1, 2, 3. So we're going to keep that 4.13. What's that 9 tell you? It tells you to round up. So our answer here is 4.14. Okay. Let's do one more. 2003 divided by 9 gives you this nice, lovely long number. How many sig figs are we allowed? 2003. Zeros are captured. They count. So you have 4 sig figs here. 9 just has 1 sig fig. So our answer is only allowed to have 1 sig fig as well. So we look at our first number, 2. What's our next number tell us? Another 2. So we leave our 2 alone. We don't round it up. Don't just write 2 here as your answer. 222 does not round to 2. Does not round to 2. Think about it. Don't move that decimal. 222, we're going to round it to 1 sig fig, is going to be 200. Okay. Please try these, guys. The only way to get good at these is to practice them. Please, 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 please practice them. Okay. We'll talk a little bit more about those tomorrow. Good luck, guys. Bye.